All right. Got a few people in here. Just cleaning off the board from the last time. Today we're going to be going over mostly just applications of the derivative, which is what test 3 will cover. There will be no linear approximation on that test. It will just be applications of the derivative and probably some antiderivatives as well. But that is not the objective of today's session. Today, our goal is to look at some specific problems. So we're going to look at some situations in which the derivative is going to be useful. Hence the name of this chapter, Applications of the derivative. So I'm just going to start with some basic stuff. I'll probably introduce the define critical numbers, get into some Rolle's theorem today. And yeah, today's going to be more conceptual stuff. We'll get to do a few example problems, but I'm going to take it nice and slow. Is this stuff, a lot of it is stuff you should be able to do already, but it is basically just taking derivatives and knowing how to read. So I'm just going to start with the first one. So this is section 4.1 in my textbook. It's probably 10.1 or 11.1 in yours. So this is called related rates. And this is kind of the whole premise of, this is a major part of the applications of derivatives. So basically you get two rates and you want to put one in terms of the other. So I'm going to read this problem, and what I like to do is every number, every numeric value that can be used when solving the problem, I normally underline it or just write it down. Because most of the information in these problems is not super useful, but first thing I'm going to do is draw a picture, because I'll make some general rules for this. Always draw the situation. You don't have to be Picasso or anything, you just have to, this is kind of far away, I'm going to bring this board a little closer just in case you guys can't see that. Let's see if I can do this without knocking all the markers on the top off. There, that should be a little better. I'll try and get it as close as I can. All right, right about there. That should be pretty good. Okay. So always draw the situation. That should be a rule of thumb that you should stick to. This is going to be a chapter in which drawing is going to be pretty important. You don't have to be Picasso or anything, just enough so you can know what's going on. And I'll explain this picture when I'm reading the problem. A lot of the applications in calculus are physics-based. So any engineering students that are taking this class, which I know that a lot of you are pre-med, so that's probably not a bunch of you, but for any engineers, this is probably going to be your specialty. And if you're an engineer, you should probably know how to draw, because a lot of your job is going to be designing. Always draw the situation, rule number one. So let's read the first example. A golfer hits a ball into a pond of still water, causing a circular ripple, as shown in figure 2, which I just drew for you. If the radius of the circle increases at the constant rate of 0.5 meters per second, so we're going to write that down. .5 meters per second. How fast is the area? That's another important detail. Of the circle increasing when the radius of the ripple is 2 meters. So how fast is the area of the circle increasing when the radius of the ripple is 2 meters? So we've got dr dt is equal to 0.5 meters per second. So let's think about what this means. Let's really take some time to think about definitions here, because this is going to be, most of the stuff is mathematically not too bad, but the definitions are the trickier part. So what this means is that the rate of change, the instantaneous rate of change, which is the definition of a derivative, for the radius is half a meter per second. So with a radius of 2 meters, we want to find out what the area of this circle, we want to know what the rate of change for the area is. So now let's think about this in terms of geometry, because really, this isn't that bad. I mean, if you think about it, right? So this formula for a circle, for the area of a circle, we know that that is A equals pi r squared, and r is our radius value. So now this shouldn't actually seem too far out there for you. And let me explain why. So this is, in a way, it's a bit of implicit differentiation, but it's a more conceptual version of implicit differentiation. So if you like concepts, big picture thinking, this is probably going to be more well fitted to you. So our strategy here is we want to get the derivative of A. And the reason I say that is because the derivative is the rate of change. So it's the instantaneous rate of change, which means what is it doing when it's moving? Like, what is the pattern? What is the slope of the slope? So our radius is 2 meters. That's what we're given. So we know that the rate of change for the radius is half a meter per second, which we're going to notate. We're going to denote this as dr dt, which is just the derivative of radius with regards to time on the bottom. So what is the area increasing? Okay, so this is not bad at all, is it? So we've got, I'm going to guess, dA dt is equal to pi times 2r dr dt. So now I'm going to go out on a limb here and say all we have to do is plug in the constants. So we know that r is equal to 2 meters. We know that dr dt is equal to 0.5 meters per second. So dA dt should be equal to, let's see, 2 times 2 is 4, times 0.5 is 2. We've got m times m, so meters per second squared. So it should be 2 pi meters per second squared, which makes sense because it's for area. So let's see the textbook, see if they got a similar solution. And yes, right on the money. So we didn't skip a beat, we got it exactly right. So the reason I didn't want to look at the textbook until the very end is to show you guys that this is probably where you want to be when you're going into a test or a quiz for something like this. And even myself, I kind of had to hesitate to think for a second, but that's what this class is about. It's about problem solving ability. So you take something really big, like a word problem. I mean, this was really paragraphs in the book. And they have their own little way for solving these. I'm just kind of walking you through my method, which is essentially the same from the textbook, but I've practiced it and rehearsed it and learned how to condense it. So this problem right here, we've got a golf ball going in the water. The splash radius is 2 meters. We know that the radius is increasing at 0.5 meters per second, and we want to solve for area. So I took the surrounding facts. I go, okay, so I know that the radius is, circle. So I go, okay, the area is going to be the area of a circle. So I go, okay, let's think about what area of a circle is, which is A equals pi r squared. So then all I really did here, guys, was I took this whole thing, and since I know that this is a physics problem, I know that our limitation is probably going to be time, and I took the derivative with regards to time, which, it also tells you what you want the bottom there to be, so it does half the work for you, and that is equal to this. And then all I did from there was I plugged in the numbers they gave us. So I'm going to go ahead and erase the board in a second here, and I'm going to give you guys just a few seconds if you got to type a quick question. Or if you're having a hard time seeing the board, you can tell me to move the screen closer, turn on some more lights, anything along the lines of that. All right, so our first rule was always draw the situation. So our second rule will be define the rates. Our third rule, find mathematical relation, i.e. area and radius, like what we just did. And this is just if you're taking notes, so if you kind of have a reference point there. Mathematical relation, and then differentiate above step. And finally, plug in numbers. So those are our basic rules for related rates. I'm going to leave it up for just a few seconds while I find a fun problem. Yeah, sure. All right, so I'm going to erase this just because I need board space. You can pause it and write them down if you need that extra time. Alrighty, so this is going to be example number 2. So the situation we have here is a spherical balloon. So like I said, step one, we're going to draw the situation. Is inflated at the rate of 10 meters cubed per minute. Find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. So a radius of the sphere, we have r equals 3, and then just so we don't forget that it's a sphere, we can draw something like that and make it look kind of three-dimensional. So we've got it's inflated at a rate of 10 meters cubed per minute. So dV dt equals 10 meters cubed per minute. Find the rate at which the surface area of the balloon is increasing. So we want to find, I'm just going to say ds for surface area, dt. We don't know what that is, but we do know that we have a radius of 3 meters. All right. So the first thing we're going to want to do here is we're going to want to find out the formula for the volume of a sphere. So we want to know V equals, and we want to know surface area as well. So volume of a sphere, let's see, that's going to be 4 over 3 pi r cubed. And then the surface area of a sphere is 4 pi r squared. See, I didn't know that one off the top of my head, so it was I might need to brush up on some of my volumes and area formulas. So now let's think about this in terms of derivatives. So we've got dV dt equals 10 meters cubed per minute. So if we take V equals 4 over 3 times pi r cubed, and we differentiate this whole thing with regards to time. So we just say d dt. So now let's take the derivative of this. So this is just going to be dV dt is equal to 4 over 3 pi times 3 r squared times dr dt. And this is just some basic implicit differentiation. You should be quite comfortable with that at this point. So we're going to cross out these 3's here because fractions. So we're going to get dV dt is equal to 4 pi r squared dr dt. So that should look very familiar. Yeah, it's almost like the same thing. Any guesses why? So I'll kind of give you guys a little quick fun fact explanation / definition for this. So that what we're saying here is that the derivative of the volume of a sphere is equal to the surface area of a sphere times the derivative of the radius of the sphere. That is what we are saying here. That is what this formula right here says. But, yeah, so this is a little bit of a weird problem here, isn't it? So then let's do the surface area next. So we'll take d, so we got, I'll just say S equals 4 pi r squared. So now let's take the derivative with regards to time. So we'll write d dt. So now we've got ds dt is equal to 4 pi times 2r dr dt. And then that's going to give us ds dt is equal to 8 pi r dr dt. So the question asked us, let's just reread it real quick. It goes, find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. So we know what radius is, and we also have defined dr dt. No, look at this. They want you to do a little bit of work. So I guess we do have dr dt. Yeah, because we can just move some stuff around here. So we got dv dt is equal to 4 pi r squared dr dt. So we know that dv dt, yeah, it's a two-parter. Look at that. There's 2 steps to this question. So we're going to plug in 10 here. So now we've got 10 meters cubed per second is equal to 4 pi times radius, which we know is 3. 3 squared is 9. So we got dr dt. I'm going to rewrite that because 4 can multiply to 9. So we got 10 meters cubed per second is equal to, let's see, 20, nope, just kidding, 36 pi dr dt. Divide this. So don't forget that pi is indeed a constant. So, gosh, that's just going to give us a gross number, but I'm going to do it on a calculator anyway. So if you don't like fractions, you should close your eyes. If you don't like decimals, you should close your eyes, because decimals can get pretty gross, and this one's, I'm having a feeling, is not going to be fun. So let's do 10 divided by, open parenthesis, 36 times, where's my pi button? Why am I doing this on an Apple calculator? If you guys want a good calculator app, Calculator X is a great one. It looks just like the TI-84, and it's free because of all the Corona stuff. So we've got 10 divided by, let's see, 36 second, where's my pi button? There it is. And let's see what we get. Yeah, so some disgusting decimal-like figure. Okay, so this is, no, you know what? I'm thinking 2 steps ahead of myself here. I'm trying to plug in numbers before we need to plug in numbers. So here's what we're going to do instead. We're just going to solve for dr dt like this, algebraically. So we got dv dt times 1 over 4 pi r squared equals dr dt. So now we have dr dt, and we can plug this right here in to this. So let's start doing that. So I'm going to work that over here because I'm running out of room as it currently stands. So we've got ds dt is equal to 8 pi times r, which is 3, times dr dt, which we just solved for. So that's going to be times 1 over 4 pi r squared dv dt. Okay. So that was not fun, but we can also plug in an R here for that. And so 3 squared is going to give us 9. So let's simplify this another step further. We got ds dt is equal to 8 times 3 is 24 pi times 1 over 36 pi. And the way I got that 36 is just r squared is going to give us 9 times 4 is 36 pi. And then we got that times dv dt, which is 10 meters cubed per minute. Look at this. This is kind of fun. So first thing you should do is realize that the 24 and the 36 are going to cancel. So now we've got ds dt. If you haven't caught on yet, that's both divided by 12. So that's going to give us, also the pi's cancel. So it's going to give us 2 over 3. And that's getting rid of that whole bar right there, times 10 meters cubed per minute. And then the final step here is to just multiply this out. So if you really want to write it as a fraction, which I know I will, it's ds dt. Actually, check this out, guys. I'm going to write it as a mixed fraction. That's what they call it. 6 2/3 meters cubed per minute. So this is the rate of change for the surface area when the rate of change for the volume is equal to 10 meters cubed per minute. If you want that as a decimal, it's 6.6666 something. And then, so now we know that this is equal to 6 2/3 meters cubed per minute. Oh, I forgot something, it would seem. Because that should be meters squared. So where did I mess that up? Well, I think my mistake is probably right about here. Yeah, there it is. Yep. Because the radius, okay, so check this out, guys. This right here, this is something you'll lose points for on a test. I just gave you a great example of how to not lose points. So let's take a look at this again, right? So I'm going to erase this work because that is not work that you should follow. That is, I forgot a step. So let's start back up from here. So the radius is 3 meters. There it is, there it is. So now surface area is going to be 8 pi 3 meters, which is really just going to give us 24 pi meters over, let's see, r squared is 9 meters times 4 is 36 meters squared times pi times 10 meters cubed per minute, which is what we plugged in for dv dt. So this right here is a mistake I just made. So now here's how this is going to go down. We're going to cancel this meters up top with that. This is now only meters to the first power. And then we're going to cancel that over here, change that to the second, and get rid of this m entirely. So now that pi is going to cancel with that one, and we're going to get ds dt is equal to 2 over 3 times 10 meters squared per minute. And then we just simplify and we get ds dt is equal to 6 2/3 meters squared per minute. So, oh, here we go. The tables have turned. I know that it's probably my 3 pre-med students watching this, but yeah, this is unit conversion chemistry. Yeah. Is that what they call it? They call it something fancy, don't they? What do they call? What do chemists call unit conversion? Dimensional analysis. That's what they call it. Yeah. So this is like dimensional analysis. If you've taken Gen Chem 1, if you haven't, you can just think of it as unit conversion. So what we're saying here is that the surface area in regards to time, so the rate of change for the surface area with regards to time is equal to 6 2/3 meters squared per minute when the rate of change for the volume in regards to time is equal to 10 meters cubed per minute. And this is all with the R equals 3 meters. So as you guys can see, I'm sure a lot of you have been asking, when would I ever use a derivative? So this is when you're going to start answering that question, because this is when it starts to get pretty interesting, the further down you derive. Because each, math tends to make sense, especially with shapes that we know, like a sphere. It's got a simple equation, we follow it through, the derivative. And this is a cool fact now too, because if you like playing trivia or something and they go, the derivative of volume the derivative of the volume of a sphere is equal to, and then you would know the answer, and you would say surface area times the derivative times the rate of change for the radius. So there you go, if you're deriving in regards to time. If not, then it's just equal to surface area. So I'm going to erase this, and then we'll work a few more of these problems because these are pretty spicy. They're not that bad. I mean, if you guys have questions, feel free to type them. I'm trying to go at a leisurely pace for this session because I think that that's how this is going to work best for you all. So let's see what we've got here. So for this one, we've got example 3, a rectangular swimming pool that is 10 meters long. So let's write that, because that's a number, 10 meters long and 5 meters wide. Has a depth of 3 meters at one end, 3 meters and 1 meter. And what this means is that the depth is changing. And they say, I'll show you guys the picture for this after I'm done reading it. So if the water is pumped into the pool at the rate of 300 liters per minute, at what rate is the water level rising when it is 1.5 meters deep at the deep end? So I'm going to draw this all out because it's probably confusing and it doesn't make sense without the pictures. So, no, that's too steep. That'll probably do it. Two meters there. This is the water right here. So we got height, length, and then this right here is 3 meters. And across the pool, from here to here, is 10 meters. And this over here is 1 meter. So if the water is pumped into the pool at the rate of 300 liters per minute, so dV dt equals 300 liters per minute. And then their question is, at what rate is the water level rising when it is 1.5 meters deep at the deep end? So what rate is the water level rising? So we want to find the derivative in terms of height. So dh dt equals question mark at 1.5 meters deep. All right, so this one right here, guys, this is tricky because you know what? You can't think in 2 dimensions for this because they also gave us width. So it's also going back that way. Five meters. Something like that. Just so you kind of have a 3-dimensional picture, kind of. But, here, you know what? There. 3D. All right, so now let's think about this. So we know that the volume is changing at 300 liters per minute. So let's think about the shape. We've got a triangular kind of prism-esque deal here. So it's going to be something like this. The shape, if you want to think about it upright, is going to be how do you draw 3D stuff? Something like that. So we know that the triangle, let's think in cross sections here, because we can't think in 3D because we're humans. So that we know that the area of the triangle is equal to 1/2 base times height. So since this is a rectangular prism or a triangular prism, then we know that the volume of that is going to be equal to 1/2 base times height times width. So they want to find out what the rate of change is for the height at 1.5 meters deep. So this is pretty tricky. So let's think about what this would mean in terms of derivatives. So obviously this right here is too many variables. So the question is how can we get less variables? So we want to find dH dt, which means that the variables we want in this equation, we're going to want them in terms of h. So the way we can do that is by moving this stuff over here. Or actually, no, we're not, wrong variable. We can solve for b from this formula, and then we can plug that in, so we'll have that in terms of h. So let's do that. 1.5 meters deep. What is the height? All right, let's see what the textbook, let's see if I can reread this real quick. See if I'm missing any key details. When you're stumped like that, just reread the question, y'all. So rectangular swimming pool, 10 meters long, 5 meters wide, depth of 3 meters, and 1 meter at the other end. Water is pumped into the pool at the rate of 300 liters per minute. At what rate is the water level rising when it is 1.5 meters deep at the deep end? So and that's what we were missing. So then we had this thing the whole time. I just forgot to write it right. So h equals 1.5 meters because it's at 1.5 meters deep, so it's going to be in terms of height. So now we have another constant that we can work with. So we know that h is a constant that we can plug in for. So let's solve for b. Let's see if we can work this out. So then we're gonna get b equals, let's see, divide by 1/2 times h, so 2a over h. So the question is does that help us? Because we're trying to plug into this and we want everything to be in terms, we want to get it down to dh dt. So we want to derive and get what the derivative of h is. And we can use h as a constant. All right, so then let's plug that into our next formula. So now we've got v equals 1/2 base times height times width. So now let's plug in for b in our formula of v. So we got v equals 1/2 times 2a over h times w. So those 2's are going to cancel right there. So now we're going to get v equals, let's see, a over h times w. So area divided by height times width. Yeah, so this is a tricky problem. So if we differentiate this whole thing, d dt, then we get dv dt is equal to dA dt, and h is a constant. 1 over h. So times 1 over 1.5, and then times w, or times dw dt. They want to find dh dt. So that wouldn't work there, would it? So let's try a different approach. Sometimes, guys, these problems are a little tricky and you can overthink them and fall down the wrong rabbit hole. And when that happens, I know it's heartbreaking, but you just got to start over. So 1.5 meters deep. I don't rehearse these problems before the sessions. I want you guys to see me make mistakes and to see me try it over and over again. So let's think about this harder now. So we know that the volume is increasing at 300 liters per minute. We want to know what the change in height is at 1.5 meters deep. So where h equals 1.5 meters. So Again, let's just set it up for volume first. So volume is equal to 1/2 base times height times width. So area multiply across the terms by h. So we know the reason this is the case is because A equals 1/2 base times height and V equals A times W. Width times length, height. So instead of using W, I'm thinking depth might be a better term for that. But let's think here. So 5 meters. So that's 2 meters. 10 meters wide, or 5 meters wide, so that's going to be constant. Okay, so then we got V equals 5 times A. So then V equals 5/2 base times height. So then dV dt equals 5/2 base, which is 10 times dH dt. So it's 50, 25 meters. So dV dt, or liters. No, meters. So we get 5/2 all age. So volume equals 5/2 base times height, but let's change base to length because that's why I was confused. I was using triangle variables for their setup, but they gave it in length and width. So read these problems carefully and try and keep a consistent form here, otherwise you'll get lost in your work, because this is a common thing to happen. So yeah, this one's pretty tricky, guys. So now we've got two triangles here that we got to think about. And then we got this guy, and I'll draw this one the opposite way so you know. Two triangles. So we've got height by length, then we've got 10 by 2 for the triangle. So then we've got 2, 10. We'll draw a separate triangle inside of that one. So what this is this is a geometry property actually, guys. It's called similar triangle. So it's saying that this and this and this and this should have a similar proportion. So you set it up as L over H is equal to 10 over 2. So you get L equals, let's see, 5 times H. So now we've got our formula for volume, which is 5 over 2 length times height, which is length, height. So now we get to do the final part of it, now that we've got all of this in terms into pluggable things that we can use, and we just do the algebra from here. So this was actually a pretty tricky problem, and I'm glad that I went over it because honestly, this is like the kind of thing y'all need to be looking for. These problems that kind of have to make you sit back and think and try different strategies for this stuff. So let's see volume here. We got V equals 5 over 2 length times height, but we know that length is equal to 5h, so we're going to rewrite this as V equals 5 over 2 times 5h times h. So then we can rewrite it again and say V equals 25h squared over 2. So we're at the final step, which is to just take the derivative. So we get dV dt equals 25 over 2 times 2h dh dt. So those twos cancel, so we get dV dt is equal to 25h dh dt. And now we can plug in, finally. So I'm going to erase some stuff right next to me so I have some extra room to write this. So we know that we got 300 liters, so H is equal to 1.5, so we got 300 liters per minute is equal to 25 times 1.5 meters times dH dt. Meters, why do I keep writing meters? Lead. No, it is meters. Oh man, that's a unit conversion, meters to liters. Whatever. So 25 times 1.5 is 25 plus 12.5, which should give you, let's see, 37.5. So meters times dH dt, divide both sides by 37.5 meters. So now we're going to get 300 liters per minute divided by 37.5 meters is equal to dH dt. So now that we're here, let's do some unit conversion canceling, because I don't know this meter to liter conversion off the top of my head. So 300 liters per minute is equal to 300 meters cubed per minute. So this right here, we can change this m to a meters cubed. That cancels there. So our final answer, guys, is dH dt is equal to 300 divided by 37.5 meters squared per minute. Or meters per minute. Oh. must have forgotten something. Oh, this is equal to 300 over 1,000. There it is. Yeah, that conversion. Okay, that's okay. So that's a metric system thing, and it actually does make a lot of sense. Their system is infinitely superior, but okay. Meters cubed per minute is equal to 0.3. Okay, so 300 liters per minute, guys, is equal to 300 over 1,000 meters cubed per minute is equal to 0.3 meters cubed per minute. So then we got times 25h dHdt. So dHdt is equal to, oh, there it is, there it is. There's the final step. Divide by 25h on both sides. Okay, so final step is, so we want to convert 300 liters per minute equals 300 over 1,000 meters cubed per minute. So now we've got that. That's dV dt. So now we're going to take that 300 meters cubed over 1,000 minutes, and then we're going to do a little flippy thing. So 25h. So now we've got divide by 25 meters squared. 25 meters times 1.5 meters over 1, which is all equal to dH dt. So we've got, let's see, meters cubes cancels with that, so that gives us just meters per minute. So now we've got 3 over 10, because those zeros, we can cancel those out. So 3 over 10 times 1 over 37.5. So we got dH dt is equal to 3 over 375 meters. That is the rate of change for the height. Now, let me check what time it is, and I'll go over and explain that work real quick. So this was actually a really tricky problem, y'all, and I'll go through and explain this nightmare here. So first of all, it just gave us the dimensions, right? What they didn't include with the directions is that this is going to be something where you're going to have that fundamental background in math, or you're going to have to study a lot for this. So this is a geometry property. So we got height in relation to length, height in relation to length. Those are both right triangles, so they are therefore similar triangles. So we set up a proportion with, let me think, right here. This is our proportion. L over H equals 10 over 2. So then what I did was I simplified and solved for L, which is just 5H. So we know that this right here, volume, is equal to 5 over 2 length times height. And the reason that is because we solve for, where is that word? We solve for width. We solve for W first. Or we plugged in for W because we knew what that was. That's right, it's 5. So we plugged in W as a constant because we don't have to worry about W. So then the length, we solved it as 5H using that proportion. So now we're left with 5V equals 5 over 2 length times H. So we plugged in 5H over here. And then 5H times 5 over 2H is going to give us 25 over 2 times H squared. So then what we do is we take the derivative of this. So that's going to give us dV dt is equal to 25 over 2 times H times dH dt, following implicit differentiation rules. Those 2's are both going to cancel, which is going to leave us with dV dt equals 25H dH dt. Now we want to get dH dt alone because that's what we are asked to solve for. So we divide both sides by 25H. So we're given dH dt equals dV dt divided by 25H. So after that, I knew that I had enough information to plug and chug. So I go, okay, dV dt is equal to 300 liters per minute, which we go up here. So if you want to make that go from liters to meters, then you're going to go divide by 1,000 and you're going to have meters cubed. So 300 liters is equal to 3/10 of 3/10 meters cubed per minute. So we were given dV dt divided by 25 times h. So the next thing I did was I divided that by multiplying it out. So I got 3/10 times 37.5. 10 times 37.5 is 375. So we got dH dt. The rate and change for the height is 3/375 meters, which I think is like 0.008 or 0.006, something along the lines of that. I'll give you guys an exact number right now. It's 0.008, yes. So dH dt equals 0.008 meters. And that is our final answer. Okay. So I won't lie, guys, that one was tricky for me just because I haven't done these types of problems in a while. This application for calculus is more useful for physics students, and I actually have taken every math class a physics student would have to take, but I have not taken a physics class yet. I'm taking my first one in the fall. So I don't really get to see a lot of problems like these, which is why I like to kind of blindside myself and go in and give it a try, because it makes you think differently. This isn't just, you can view this class as a punishment and view it as a burden that you have to study all the time, or you can think about it in a positive half glass full kind of way and go, you know what, this class is a lot of work, but this is actually a pretty neat skill I'm learning here. And it's not even just a skill, because if you're not a physics major, you're probably rolling your eyes at me, but hear me out. Everyone needs to know how to solve problems. That's why this stuff, like, I keep this stuff and I come at it with everything I have, and I just think with intuition. I think with just the rules I know, and I work at it until I do it. I can do physics problems for differential equations, not because I've taken physics classes, but because I chose to approach these problems and I chose to accept that I was going to make mistakes along the way. And that's a very important aspect of learning calculus, is that this class isn't just doing math like high school. It's very different from high school. Honestly, this is one of the coolest classes you'll take if you've never taken another math class again. This is one of the coolest classes you'll take in your major, probably, if you're pre-med or something like that. Because this is going to teach you how to think differently. And, they like, even health benefits, guys, math is there. Like, this is if you do this, I like to do these types of problems, just simple, like derivatives, calc 1 type, some integrals if I'm feeling it. I do those when I'm drinking my coffee in the morning, guys. Like, it's just because that stuff is so healthy for your brain and just keeps you focused. It prevents dementia, Alzheimer's. I don't want to have to go on a little TED talk about why math is good for you, but I hope this session was helpful for everyone that came. And if it didn't make sense, I wouldn't worry about it quite yet. This is a pretty tricky problem. I intentionally chose some to challenge both myself and you guys, the students taking the class, because I want you guys to be able to solve the hardest problems that are thrown at you in a test. And the only way to do that is by practicing those problems. So if you don't think you did good on test 2, which I know was a pretty difficult test for a lot of students, then you should really be studying for this, because the only difference between a student getting an A in this class or a B in this class or whatever grade they want is them deciding to get that grade. This isn't out of your hands, guys. This is math. This is something that can be done. I know that this is an intimidating course, but I think a lot of you will pull through and finish with a grade, with whatever grade you choose to finish with. So that's all I got to say for today. I hope you guys enjoyed the session. If you have any questions about this stuff, feel free to just message me after the session or comment it or something. But yeah, that's it for today, guys. So thanks for coming. I'll see you all on Sunday probably.